Hi everyone, welcome to Booster Chemistry. Today we will study a new topic, that is stereochemistry. First, there are so many important areas from which questions are getting asked repeatedly. We will go one by one. First, we will start isomerism. We all know compounds having same molecular formula but different physical and chemical properties are called isomers, and this phenomenon is known as isomerism. It is broadly classified into two types, that is configurational and conformational. So first one is configurational. We all know carbon has valency 4. That means it can be bonded to 4 groups. If all these 4 groups are different, we will call it an asymmetric center or chiral carbon. Suppose here carbon is bonded to 4 different groups. We keep 2 bonds fixed and exchange the remaining 2. Then what we obtain is called as configurational isomers. Suppose here we keep bromine and OH bond fixed and exchange between CH3 and NH2. Then what we got is called configurational isomers of the starting compound. Both are different molecules. Then conformational. Conformational means here we have to keep one bond fixed and rotate the remaining 3. Suppose we keep this bromine bond fixed and rotate the remaining 3, it can be clockwise or anti-clockwise. Suppose we rotate clockwise, that means CH3 can go to this position, OH can go to this position, and NH2 can go this position. Then these are called conformational isomers, and both are identical molecules. They only differ in the direction of watching, from which direction we have watched. So next one is then configurational isomers are classified into two types on the basis of connectivity. Connectivity means position of groups. It can be functional groups or substituent or double bonds or triple bonds. So if these are same, we will call it stereoisomer. If different, we call structural or constitutional isomers. This is of less important, but most important is stereoisomer. Among these two, optical one is most important. So structural or constitutional isomers are of different types like chain isomers, position isomers, functional isomers, metamergem, ring chain, and tautomergem. Stereoisomer again is of two types. One is geometrical, another is optical. Geometrical again is of three types. One is cis trans, another is sin and p. Next one is E and Z notation. So we will go one by one. First we have to learn a rule on the basis of which we have to assign the priority order. That is Kahn-Ingold-Friedlander rule or golden rule. Basically, these are three scientists who proposed these rules. So for determination of priority of different groups or atoms attached to the carbon atom or any other atom, first the group or the atoms having higher atomic number will get first preference. If the atomic number remains same, then we have to see the atomic mass. Higher the atomic mass, first will be the priority. Then atom will be preferred over lone pair, cis will be preferred over trans, R will be preferred over S. Next, M will be preferred over P. Then there is a rule of replication, that is when the group bonded to double bond contain multiple bonds, then the N group or atoms which are assumed to be bonded that most times to the group. Suppose here is a cyanide group, so we have to break the pi bond. There is a sigma bond between carbon and nitrogen. There is 2 pi bonds between carbon and nitrogen. Suppose we break first pi bond. Since carbon is bonded to nitrogen, so we will give carbon to nitrogen, and nitrogen is bonded to carbon also, so nitrogen will get carbon. Then again break another pi bond. Carbon is bonded to nitrogen, so carbon will get nitrogen. Nitrogen is bonded to carbon, so nitrogen will get carbon. These are called phantoms. Similarly, here is a C triple bond CH. So we will break the pi bond. Here is 2 pi bond. So first we will break 1 pi bond. Carbon will get carbon. This carbon will also get carbon. Similarly, break the second one. Carbon will get the carbon. This carbon will also get this carbon. So here is CC. Here is CCH. Since here is a C, that means carbon having atomic number more than that of hydrogen. So CCC is preferred over CCH. If the bonded atoms are same, then C the next atom. If next atom is also same, then C next, and so on and so forth. Next one is geometrical isomers. These are basically arises due to restricted rotation around C double bond C, C double bond N, and N double bond N. These are three types. First one is cis trans, next EZ, and syn anti. Cis trans. Cis trans arises due to restricted rotation around C double bond C. There is a condition to exhibit cis trans isomerism, that is, molecule must contain C double bond C, that means it must be planar. Next one is it must have two different groups or atoms bonded to it. Then if the same priority groups are bonded on same side, that is, if there is angle of 90 degree between this same priority group, then it is cis. Suppose here we give the priority according to CIP rule. Here is carbon, here is hydrogen. Since atomic number of carbon is greater than that of hydrogen, carbon will get first priority, hydrogen will get second. Similarly, here carbon will get first priority, hydrogen will get second. Since same priority group are on same side or there is an angle of 90 degree between these two, it will be cis. In the case of E and Z, it basically arises due to restricted rotation around C double bond C. But here is a difference, that is, all the four groups attached to carbon must be different. If same priority groups are on same side, that means the angle is 90 degree, then Z. Suppose here in one side there is OH and bromine. First we see oxygen and bromine. Since atomic number of bromine is greater than that of oxygen, it will get first priority, OH will get second priority. Similarly, since atomic number of carbon is greater than that of hydrogen, it will get first priority, hydrogen will get second priority. Same priority group are on same side, so it is J. Similarly, in syn anti, it arises due to restricted rotation around C double bond N, that is oxime, or N double bond N, that is azo compound. In oxime, we will see on the basis of H and OH. If H and OH are present on same side, it is syn. If on different side, it is anti. In cis trans, if same priority groups are on opposite side, that means if there is an angle of 180 degree between these two groups, then it is trans. Suppose here between carbon and hydrogen, CH3 and H, since atomic number of carbon is greater than that of hydrogen, so it will get first preference, because so CH3 is number 1, H is 2. Similarly, here CH3 number 1, H is 2. 1, 1, same priority are on opposite side, or there is an angle of 180 degree, so it is trans. In AZ, if same priority groups are on opposite side or 180 degree, it is E. Suppose here between OH and bromine, since atomic number of bromine is greater than that of oxygen, so bromine will get first preference, it is 1, it is 2. Here between carbon and hydrogen, atomic number of carbon is greater than that of hydrogen, so it is number 1 and it is number 2. Since same priority groups are on opposite side, it is E. In syn anti, in case of oxime, if hydrogen oxime, in oxime, if H and OH are on opposite side, it is anti. Here is the example. Then we have to see azo compound. Azo compound basically contain N double bond N. Since nitrogen has one lone pair over it, and lone pair is less preferred, or atom is preferred over lone pair. So in azo compound, if same priority groups are on same side, it is syn. If on opposite side, it is anti. Here is the example. Nitrogen contain lone pair and here is the phenyl group. So since atom is preferred over lone pair, it will get first priority. Lone pair will get second. And since same groups are on same side, it is syn. Similarly, here in same groups are on opposite side, so it is anti. It is quite difficult to imagine the molecule in 3D. We have to represent them in 2D. So we use so many projection formula. Here are the 4 important formula. We will go one by one. First we will start flying wedge projection formula. Basically this representation is for flying wedge projection. Here the solid line denotes the atoms or the groups are on the plane. The dash line will denote the atoms below the plane or away from the observer. Similarly, the wedge line denotes the atom is above the plane or towards the observer. Next one is sawhorse. This is the representation for sawhorse. Basically, the solid line represent the atom on the plane. Dash line represent atom below or left or away or backside. The wedge basically represent atoms or groups are above or towards us or in the right or in the front. So here is the different representation of sawhorse projection. We'll do one rotation. we'll do one rotation. Suppose here is the three atoms A, B, C attached to each group. We know this circle is 360 degree. That means each angle contain 120 degree. That means angle between A and B is 120 degree. Suppose we have to rotate this molecule in 120 degree. A will come in the place of B. B will come in the place of C. C will come in the place of A. This is what we obtained. Since it is total of 180 degree, that means half will be 60 degree. So if we rotate 60 degree, C will come to this position, A will come to this position, B will go to this position. This is what we obtained. We know the angle between A or the angle of a straight line is 180 degree. That means if we rotate this molecule to 180 degree, C will be exact in the opposite of it. A will be exact in the opposite of it, B will be exact on the opposite of it. So this is what we obtain after rotating 180 degree to this molecule. Next one is Newman projection. This is the representation of Newman projection. This dotted line denote front carbon. This is the molecule on the plane. This is above or on the right side. This is on the back side or left. The circle represent the backside carbon. This wedge represent the molecule or atom on the right side or front. This dashed line represent the atom or molecule on the left or back side. Solid line represent the atoms or molecules around the plane. Since the angle between two molecule groups are 180 degree, this is basically called as staggered. Here, since CS3 both are bulky and at angle 0 degree, these are called eclipsed. We can convert this formula to Sawhorse formula. This is the representation of Sawhorse from Newman projection. Next one is Fisher projection. There is certain rules while writing or while representing the molecule in Fisher projection. First one is the most oxidized group should be on the vertical line. This is the vertical line, this one is the horizontal line. Most reduced group should be below the vertical line, that means on this side. Maximum number of carbon atoms should be on the vertical line. This is the general representation of Fisher formula. This is a general notation. We can assume that the vertical line represents the dash and the horizontal line represents the wedge. So this is right side or front. This is also right side or front. This is left side or back side. This is left or back side. If you do 180 degree rotation, the vertical atom will come. The top atom will come to bottom and bottom will go to top, and there will be diagonal exchange of atoms or groups if you do 180 degree rotation of the initial projection. Then there is interconversion of different projection. First we will go from Newman to Fisher. See, this is the only projection which can be directly converted to Fisher. So whatever projection or whatever structure is given, we have to convert first to this formula or this projection, then this can be directly converted to Fisher. Suppose here is the example. It is not in the format, so we have to do this format by rotating the front side molecule to 180 degree. So this is after 180 degree rotation, CS3 will come exactly opposite to it. OH again come exact to opposite to it. H will go exactly opposite of it. So this is what we get after rotating the front carbon to 180 degree. So this is the Newman projection. It can be converted to Sawhorse. So this is the front carbon, this is the back carbon. We know in Fisher maximum number of carbon atoms should be on vertical lines. So by rotating such angle, we have to bring maximum number of carbon atoms on this vertical line which is there in this molecule. So we can directly convert this to Fisher. So first this carbon is carbon number 1. On the right side there is OH, so here is OH. On left side here is H, so here is H also. Then second carbon, on second carbon right side there is Cl, here is Cl. On left side there is bromine, this is also bromine. So this is the complete representation of Fisher formula from Newman projection. Next one is from Sawhorse to Fisher. These are different types of Sawhorse representation. So convert it all to this format. Then write to this according to Fisher projection. Fisher projection means This carbon atom 1, this will be 1. This is right side, this is right side, this is left, this is left, this is right, this is right, this is left, this is left, and maximum number of carbon atoms should be on vertical lines, should be on this plane. Here is an example. So here we convert this molecule to this format. That means we have to do 180-degree rotation of the carbon number 1. So 180 means CH3 will come to exactly opposite to it, where bromine will come exactly opposite to it, OH will come exactly opposite of it. So this is what we get after 180-degree rotation. Now we have to represent this in Fisher projection. Here maximum number of carbon atoms are on the plane, so we have to represent it. Here is the carbon number 1, here is the carbon number 1. On right side, here is bromine, here is also bromine. On left, OH, here is OH. Similarly, on carbon number 2, on right side, there is hydrogen, here is also hydrogen, here is chlorine, here is chlorine. Next, from Newman to Sawhorse. So, by removing this circle and exactly by joining a solid line, we can convert from Newman to Sawhorse. Then, from Sawhorse to Newman, here is the projection, here is the front carbon, and the circles represent the backside carbon, that is carbon number 2, and here is the atoms. So these are different representation of Sawhorse to Newman by drawing a circle which represent the carbon number 2. Next one is from West to Fisher. Here is the West representation. Dash line denotes the atom on the back side. West line denotes the atom on the front side, and solid line represent the atom on the plane. So here ethyl group is on the plane, bromine on front side. That means bromine on front side. Hydrogen on back side, that means hydrogen on back side. Similarly here carboxyl group is on the plane, NH2 amine group is on the back side, that means on left side. OH hydroxyl group is on the front side, that means OH on front. So we have to represent to Fisher, that means maximum number of carbon atoms should be on the plane, and this OH formula must be in this format. So we have to rotate the second molecule to 180 degree. The COH will come exactly opposite of it, NH2 will go exactly opposite of it, OH will go exactly opposite of it. So this is what we get after 180 degree rotation of this molecule. Now we have to represent this to Fisher projection. So this is carbon number 1, this is carbon number 2, and maximum number of carbon atoms are on the plane. So this represents the vertical line. Here it is carbon number 1. On carbon number 1, bromine is on right side, here bromine is on right side, hydrogen is on left side. Here in carbon number 2, NH2 is on right side, OH is on left side. Next, from Fisher to S, suppose here it is given the Fisher projection, we have to convert it to OH. That means suppose we have to bend the molecules towards bromine side. That means CH3 and C2H5 ethyl group both should be on the plane. Bromine should be above and fluorine should be below. Here if you bend the molecule towards fluorine, both CH3 and C2H5 should be on the plane. Bromine should be above, bromine should be below, since we bent it towards fluorine in front side. That means fluorine will be on front side or OH. Next is determination of RS configuration. This is very important from both get and get point of view. So R stands for reactors, means clockwise. S stands for sinister, means anti-clockwise. So there is different groups, different cases. We will go one by one. First, we have to assign all the groups or atoms present in the molecule on the basis of CIP rule. First is case 1. If the lowest priority group is present at the bottom position, then rotate the I in decreasing order of priority. If the rotation is clockwise, then it is R. If the rotation is anti-clockwise, it is S. Suppose here is the example. Here is the carbon atom, which is sp3 hybridized, bonded to 4 atoms of different nature. Here all are sigma bonds, so we have to give the priority on the basis of CIP rule. First, we will go from atomic number. Higher the atomic number, more will be the priority. So bromine will be the first one, then chlorine, then fluorine. Fourth is hydrogen. Hydrogen is present below the plane, so there is no need to change. So we will rotate in decreasing order of priority. 1, 2, 3. That means it is anti-clockwise. S. This is in OH formula. For suppose here is an example of Fisher projection. This is the general notation of Fisher projection. That means the vertical line denotes below the plane and the horizontal line denotes the above the plane or OH. Suppose here we have to give the priority on the basis of safe rule. Iodine will get first, bromine second, chlorine third, then hydrogen is fourth. Since hydrogen is present on the vertical line, that means below or dash, so we'll rotate on decreasing order of priority 1 to 3. This is clockwise, that means R. Then second case, if the lowest priority group is at above position, then we have to reverse the configuration whatever is obtained. Suppose here is the example. Here we have to give the priority on the basis of safe rule. Bromine will get first, chlorine second, fluorine third, hydrogen is fourth. But if we rotate without changing hydrogen, this will be 1 to 3 anticlockwise S. But here hydrogen is present above the plane, so we have to change it. That means it will be R. Similarly, in Fisher projection, we have to give the priority. Iodine is priority number 1, bromine second, chlorine third, hydrogen is fourth. If we don't change, this will be 1 to 3 clockwise R. But here hydrogen is present above the plane, so we have to change whatever is obtained. That means it will be S. Then case 3, if the lowest priority group is present on the plane, then we have to do even number of interchange so that the lowest priority will come below the plane. Even means 2, 4, 6 onwards. If you do odd number of interchange, then these are different molecules, not identical molecules. Suppose here is the different groups. Bromine will be first priority, chlorine second, fluorine third, hydrogen is fourth. Fourth priority is present on the plane. Suppose we have to denote it like this: 1, 2, 3, 4. Here the third group is present below the plane and 1 is present above the plane. So we have to interchange between these two and these two also even number of times. That means 2 times. So 2 will go to this position, 4 will go this position. Then rotate in decreasing order of priority 1, 2, 3, 4. This is anticlockwise, that means S. Since this is a very long topic, so we'll divide it into 3 parts. This is part 1. Next I will upload part 2, then part 3. So if you have any doubt, please let me know in the comment box. Thank you so much for watching. If you like the video, give us a thumbs up. Please subscribe. Thank you so much.